Morning, good afternoon, or good evening, whenever you're watching this. In this video, I'm just going to cover one last little topic on waves that I don't think we've covered yet, which is the subject of diffraction. Now, every year I teach this, and people always seem to get confused between diffraction and refraction. We've already seen refraction. Refraction is the change in speed and therefore direction as light goes from one medium of one density to a medium of a different density. And above my head, I've given you the definition of diffraction. Diffraction is the spreading out of wavefronts as a wave passes through a gap or over an obstacle. So therefore, diffraction is not the same and it's not related to refraction. Please don't get the two things confused. Let me start by giving you an example of diffraction, which I've already said is the spreading out of waves, or wavefronts. If you have a door that's open with a small gap, with a bright light on the other side, as light comes through the gap, it will spread. You can see here on the floor the light is spreading out. That's diffraction. It won't spread very much. So for example, if there's somebody standing on just the other side of that gap, slightly to one side, you won't be able to see the person because the light won't bend around the door that much. However, if that person was to shout, you would be able to hear that person. And the reason is that sound will diffract or bend much more than light. And the reason for that is that sound has a much longer wavelength than light. So before I go any further, you can already see that the amount of diffraction you get from a wave is related to its wavelength. The longer the wavelength, the greater the diffraction you will see in general. Okay, here's a nice example of diffraction in nature. This is an entrance to a harbour. That's an aerial photograph. I thought it was a natural harbour, but this might be concrete. I'm not quite sure. And you can see that waves are heading towards the beach in this direction, going through this gap and carrying on to the beach. I'm not sure you can see it very well, but I can just about make out the tops of the waves here, or the wave crests. And wave crests we can refer to as wave fronts. So crest, maybe there, crest, maybe there, crest, so on. Maybe one there just before it hits the harbour. Okay. So the distance from wavefront to wavefront is the same, or I've not drawn it very well, but that should be one wavelength, and that should be one wavelength, and they should be the same, same size wavelength. The waves hit the gap, and you can make out here, as they go through the gap, they start to bend, or they start to diffract, like that. So now, I don't think I've done a great job of showing those waves bending. You can make it out in the photograph though. But what I tried to show was that this wavelength, those distances should be exactly the same before the wave goes through the gap and after the wave goes through the gap. Because during diffraction, diffraction will not affect wavelength of the wave as it passes through the gap. It will not affect the speed of the wave as it goes through the gap, and it will not therefore affect the frequency. Nothing about these waves is different after the gap compared to before the gap, other than they've diffracted or the wavefronts have bent. It's very important to remember that, please. There's no changes to the characteristics of the wave other than the bending. Okay, I've tried to show this a bit more clearer in a little diagram I've drawn here. You can see wavelength stays the same, but you get the bending of the wavefronts and diffraction. However, what I've done in the second diagram, I've reduced the size of the gap, and now this gap, the size of this gap is much closer to the size of one wavelength, and therefore you get much bigger diffraction, much more bending of the wavefronts. And that's the other thing you need to remember, please. The closer the size of the gap is that the wave is passing through to the size of one wavelength of the wave, the more diffraction you'll get. Here, this gap is much bigger than the size of one wavelength, so you get a small amount of diffraction. Here, much closer to the size of one wavelength, so you get maximum diffraction. Okay, that just about covers everything that's on the syllabus with regard to waves going through gaps. We just need to discuss now what happens when a wave goes over an obstacle. So here's a nice example. Here's a house, presumably with somebody inside. There's a hill, and an explosion will take place on the other side of the hill. The person in the house will not see the explosion or the flash of light because the light will not diffract very much. However, the person will hear the explosion because the sound bends much more, diffracts much more, and reaches the person in the house. Compare that to a radio wave. Radio waves have quite a big range of frequencies and wavelengths, up to hundreds of meters. If we take a radio wave with a small wavelength and therefore a very high frequency, and we've got a radio transmitter in this case on the other side of the hill, the person in the house won't be able to pick up that radio station on their radio because with these high frequency radio waves, not enough diffraction is occurring to bend the wave to the antenna at the house. However, replace that radio wave with a much longer wavelength wave. Longer wavelength waves diffract much more as they go over an obstacle, in this case the hill, and the person in the house will be able to pick up the long wavelength radio wave on their radio. Okay, so that just about covers everything that we need to know about diffraction. So just to recap, diffraction occurs as waves go through gaps or over obstacles. As they go through gaps, they diffract and the wavefronts bend. There's no change to frequency, wavelength or speed. The only change is the bending of the wavefronts. The closer in size the gap is to the size of one wavelength, the more diffraction will occur. And as waves pass over obstacles, as they pass over the obstacle, they will diffract. And the longer the wavelength of the wave, the more diffraction will occur as it passes over the obstacle. But again, like we saw before, there will be no change in wavelength, frequency or speed of that wave. And all types of waves can diffract, including light, sound, and water waves, and so on. Okay, so I hope that was helpful. We'll go over this in the class when I see you. And like I always say, take care of yourselves and your family, and I will see you in our lessons. Okay, goodbye everybody.